Okay, so as we jump to chapter 5 here, we have a little bit more of an exploration to do with trig. And the first thing we're going to do starts with proofs, essentially. Proving that two things are equal. If you look down at exercise 1, we're trying to verify that's proved that this will equal this. And if we look at all of this stuff, this is what we know so far. Here's all of our reciprocal identities, so we can always like substitute out a sine x and replace it with 1 over cosecant or vice versa. The Pythagorean identities you haven't seen in a while. This one, yes, we talked about last chapter, sine squared plus cosine squared equals 1. But you also need to know these two Pythagorean identities. They will not be on your reference sheet. None of these three will. None of this stuff will, to be honest. But this one I'm pretty confident you know. And the way you get to these other two is just simply, if you don't remember them, you can just divide everything here by sine squared. And when you divide by sine squared by sine squared by sine squared, it's going to turn into this one. So sine squared divided by sine squared is the 1. Cosine squared divided by sine squared is cotangent squared. And 1 divided by sine squared is cosecant squared. So that'll get you to this one. And if you divide everything by cosine squared, it'll get you to this equation. Sine squared divided by cosine squared would be tangent squared. Cosine squared divided by cosine squared gives you your plus 1 equals, and 1 divided by cosine squared gets you your secant squared. So you can get all three of those if you just really remember this one. And then your even and odd identities, because sine is odd and because tangent is odd, we get this property with the sines, cosecants, tangents, and cotangents. And because cosine is even, we get that the cosine of negative x just equals cosine of x, and the same for secant. I don't know that we'll use those as often, but I just reminded you of kind of all the properties you know so far. So on a verify one, ideally you'll only have to work on one side, take the more complicated side and simplify it. But definitely as these get harder, you're going to have to manipulate both sides. But the key is, you're trying to prove that they're equal. We can't do anything that assumes that they're equal, like any of our solving techniques, like dividing by something on both sides. We can't do that in a proof. You can do that when you're solving, not in a proof. All you have to do is kind of treat each side independently. So simplify the left, simplify the right, and see if they're equal. So with something like secant, I would first substitute in a 1 over cosine x times, and cotangent is cosine x over sine x. And then your cosine x's are going to cancel, so you're going to get 1 over sine x equals, and you can either change this side to 1 over sine x, and so you'll have 1 over sine x equals 1 over sine x, or you can go one more step with the left side and make this a cosecant x. And then you really aren't changing your right-hand side at all. It really doesn't matter, because you can change both sides. So when I read through these and grade these, number one, every single step needs to be very well documented. The doing things in your head part can't happen here, because it's all about presenting an argument that step by step by step can be followed. Kind of like proofs in geometry, as much as you knew how obvious the fact of the matter was that you were trying to prove, you had to verbalize every single step. And so we do that showing work and showing substitutions here, and you cannot skip steps. And you really need to do just one thing at a time, not doing a whole bunch of substitutions and cancellations in one step. And then you just put your check mark, show that they're equal, and you're done. So on exercise 2, I'm going to change the tangent into sine x over cosine x. Can't really do much with cosine x, and I'm going to leave the right-hand side for now. Now this is interesting because I have a multiplication. That's going to change it to sine squared x over cosine x plus cosine x. And in order to do anything with this, I would need to get a common denominator, because I can't add these unless I have a common denominator. So if I put this over 1, it's going to need a cosine x, and the top's going to need a cosine x. So I'm going to make it cosine squared. So now up top, I have sine squared x plus cosine squared x, which is just, from our identity, 1. So this becomes 1 over the common denominator of cosine x. And then again, this was secant x. I'll do this one a little bit differently. You can change the secant x to 1 over cosine x, and then 1 over cosine x, and you're done. You almost go into these blindly. You don't necessarily know the way it's going to pan out, but you start substituting things out, realizing things cancel, and so on, and often it just comes together. So on this very next one, it's already in terms of sines and cosines. If you've noticed on the first two examples, the first thing I did was get everything in terms of sines and cosines. This one already is. But on the binomial on the left, I see that both pieces of the binomial have cosine x. So I'm going to factor that out. And when I do that, I have a 1 minus sine squared, which may not pique your interest now, but the more you look at these, they will. And the 1 minus sine squared x comes from, we're going to utilize this, because these Pythagorean identities can be used exactly as they seem, or we can manipulate them. So if I kind of thought about this one and subtracted sine squared x from both sides, that would cancel, and 1 minus sine squared x can be replaced with cosine squared x. So I'm going to go down here and replace that. And then cosine times cosine squared, in fact, makes cosine cubed, and I'm done. And you're probably thinking, how am I ever going to know to do that on my own? And early on, you probably would not ever see that. Some of you might, but most of you wouldn't. The more that you do and practice, you are going to get used to kind of different things to look for. And for choosing these examples, I tried to pick, a good variation of the different skills you'll have to use on the homework problems that you're assigned. So when you're looking at your homework, there should be one example on the note sheet today that kind of parallels it in some way and does something similar to what we did today. Okay, and also I will add to that there are multiple ways to do the same problem. There's not just one way to prove it. So everyone's work on a proof I'd have to evaluate separately. So on this next one, I do have sines and cosines on the left, not on the right. So I'm actually going to start with a right here and make this 1 over cosine, and this one sine theta over cosine. And actually, with adding fractions, they already have a common denominator, so I'm just going to add them. And actually, I'm done. That was pretty simple. Kind of fell together for me. I got lucky. It fell together and into place, and I didn't need to do much more than that. Okay, on exercise 5, one thing I can do, and this is where they get a little bit more challenging, is take a peek at those denominators. I could attempt to get a common denominator on the left-hand side. So this one would need a cosine x. I don't know if it's going to work, but I'm going to try it. This one would need a 1 plus sine x. Okay, so I get cosine squared x plus, and when I FOIL this out, I'm going to get 1 plus 2 sine x plus sine squared x all over cosine x 1 plus sine x. And then on the top of that numerator, I have cosine squared x plus sine squared x, which is 1. So I have 1 plus 2 sine x over cosine x, and then 1 plus sine x. And as far as like skipping steps and making sure you document something, here's a perfect case in point. I would never allow you to put just 2 here right away. Eventually, yes, but not right away, because I want to see that the 1 stayed, the plus 2 sine x, I want to see that sine squared plus cosine squared was replaced with 1. And if you put 2 plus 2 sine x right away, I'm not going to see that. You know, I could figure it out, but it would also take me a decade to review everyone's proof if we were skipping steps like that. So that's kind of what I mean by documenting every single step, even when it's tedious. So now I'm going to make this 2 plus 2 sine x over cosine x. I'm running out of room here. Hopefully maybe you can see a little bit of what's going to happen, because in my numerator I can factor out that 2 and I get 1 plus sine x over cosine x, 1 plus sine x. The 1 plus sine x will cancel and I get 2 over cosine x, which if you look at the right hand side, secant is 1 over cosine x, so that becomes 2 over cosine x. And so 2 over cosine x equals 2 over cosine x. It's a little bit sloppy because I ran out of room. You want to do these vertically, keep everything lined up, so you see the track exactly what the left side does. Unfortunately, I ran out of room, so I had to go a little bit to the right, but I think you get the idea of the proof there. Okay? In exercise 6, I'll reiterate why we can't solve here. Some of you might have the instinct of cross-multiplying. Cross-multiplying is a solving technique. It runs under the assumption that they're already equal, and therefore I'm solving for what x is. We cannot do that here. We can't run under the assumption that these are already equal. It's in fact what we're trying to prove. So again, what we can do is we can get a common denominator. On the right side, we need 1 plus cosine x. And then we get sine squared x over sine x, 1 plus cosine x on the left. On the right, we're multiplying conjugates, so that's just 1 minus cosine squared x over sine x, 1 plus cosine x. And then this 1 minus cosine squared x, if we go back to the front again, I can kind of do something similar to this Pythagorean identity that I did the first time. And you can envision this, if I subtract cosine squared x over, 1 minus cosine squared x will equal sine squared x. So I'm just going to replace this with sine squared x, and I will be done. I do realize that both sides can be simplified, but it doesn't matter. That's not what we're here to do. We're here to prove that the sides are equal, so I don't need to cross out a sine x. Exercise 7. You got a tangent. You could try a sine over cosine, but you'd have a complex fraction, which I want to stay away from. One technique that can tend to be helpful is multiplying by conjugates of a denominator, and I'll show you in a minute what that does for us. Before doing that, though, I'm going to capitalize on the fact that sine of negative x is odd, so that negative would kind of come out in front, and it would change this to a plus sine x. So now on the denominator here, if I multiply by the conjugate, what's going to happen is, this might be a little ugly, but that's okay. Let me go with it. Again, it might not be right. I'm just trying to show you this conjugate technique. My denominator becomes 1 minus cosine squared x when I FOIL that out. And that's the same as 1 minus cosine squared x is the same as sine squared x. I'm trying to think what I want to do with the top right here. I might change that tangent to sine over cosine. recording because I'm actually going to be absent today. The kiddos are sick, so you can come in and listen, but I am recording. So if I am right here on the top, I'm seeing that they both have a sine x, so my gut is to try to factor that out, which I can do. I'm going to take it way out in front. And then I'm going to have, I'm taking out that sine x, so I'm going to have 1 over cosine x, which will be secant if I get there. And then the sine x will cancel with the squared. So let's see where I am here. Lack of room again. 1 minus cosine x. And I can make that 1 over cosine here secant x plus 1 all over sine x. Okay. I'm going to, again, this is ugly and I don't really have great direction right now, but I'm just going to keep chugging through this and see what happens. So 1 times secant, I might, do I want that cosine? I'll keep it secant because I just made it secant. And 1 times 1, then minus cosine x secant x, and minus cosine x. I'm foiling up top over sine x. I think I'm going to go back to, well, this secant is going to be 1 over cosine. Which will be nice because that'll just become minus 1. And then the plus 1 and the minus 1 will cancel. So that just did a whole lot. So now I'm down to secant x minus cosine x all over sine x. Okay, still not great. I guarantee if I took a longer look at this and wasn't in such a hurry, I could find a faster way, and maybe I'll show you that tomorrow. But in the meantime, I still think we're making good progress towards tangent x. That's our goal. Secant x, I'll make 1 over cosine x minus cosine x all over sine x, and I think I'm going to try to get a common denominator up top, so give this a cosine x and a cosine x. So the numerator is going to become 1 minus cosine squared x over cosine x, all divided by sine x, and I can keep change flip. When I keep, this is the same thing from our identity on the front as sine squared x. So I'll have sine squared x over cosine x. Here's my keep, change, and flipping sine to 1 over sine. Oof. And my sine here is going to cancel with my squared there. And I'm left with sine over cosine, which is tangent of x. And then, if you go back to the beginning, that was what I had. That was not at all the most efficient way, but it is, of course, working. Just, again, maybe we'll revisit that tomorrow and see the faster way. And at this point, we've run out of time, or not time, necessarily space. And so I'm going to jump into the book and show you where I pulled exercise 8 from. And I'm hoping that it's done out in the book already. So 5.1, give me 1 minute to do that. Yeah. Okay. So just follow along here. If you want to write it on a separate sheet of paper, you can. But this is example number 8 from the book. And I'll do this. So let's kind of see how they do it. They start with the left side, and I believe, what do? They're going to get a common denominator. So this one gets a 1 minus cosine x, and this one over here gets a 1 plus cosine x. So now they have a common denominator. And then their numerators can be added. So on the numerator we have 1 minus cosine theta plus 1 plus cosine theta all over the common denominator. In that numerator, you can cancel the negative cosine theta and the positive cosine theta. So that just puts it at 2 over, because they were combining the 1 plus 1 at the same time. Okay, so there's our 2 over 1 plus cosine theta, 1 minus cosine theta. So we're going to multiply out the denominators, 1 minus cosine squared theta. That's a Pythagorean identity. Although, look at, they don't actually touch that. They stop there and they say, now we're going to work on the right side. So they're taking the right side, which was the 2 plus 2 cotangent squared. And they factored out no, they didn't factor out anything. They changed the cotangent squared. So there's your 2 plus 2. And they changed it to cosine squared over sine squared. Then they got a common denominator, so they put this over 1, and then they make the denominator sine squared, and they give the top a sine squared, so this 2 becomes 2 sine squared over sine squared, plus, and they just multiply this 2 through 2 cosine squared over sine squared. So they have a common denominator, and now they add their numerators, and then they factor out a 2. Sine squared plus cosine squared is left in parentheses, which is just 1. 2 times 1 is 2. And so we have 2 over sine squared on the right. And then, so they left 1 minus cosine squared. They could have made that 2 over sine squared back there. But instead here, the 2 over sine squared, they went backwards. And they made the sine squared the 1 minus cosine squared. So both sides, the left side became 2 over 1 minus cosine squared. Their right side became 2 over 1 minus cosine squared. So, again, a little variation. I probably would have done mine slightly different, but that's okay. That is just as well, and there is a couple different ways you could do it. Here's that last one that I was talking about. See how they did it differently. So they began with the left side, tan x minus the sine of negative x, and what did they change first? Oh, they handled the odd sign situation like we did, so that double negative is going to become a plus. Okay? So now they're here. Next step. Right here. So they changed their tan and the sine over cosine. And so they created their complex fraction a little bit earlier than I did. I was trying to avoid that admittedly at first. Then they get a common denominator in their numerator, so they gave this a cosine x. Cosine x on this term. So there was a common denominator, so their numerator is about to become sine x plus sine x cosine x all over that common denominator. There we are. So then maybe, let's see if what do they do next? Yep, they rewrite it as division, and then they're about to keep change flip. They keep change flip. I'm going to guess, because I see this 1 plus cosine, that they're going to factor out a sine to get the 1 plus cosine. Sure enough, that's what they do. They factor out a sine up here, and their 1 plus cosines cancel, and then they're just sine x over cosine x, and they are done. Becomes tangent of x. So that's all for today. Your homework is written there at the bottom out of the book, page 578, 1 through 7, 1 through 3.